Hello, good morning, and welcome to the Series A webinar. I think the topic of today is a very exciting one, the role of artificial intelligence and surgical robots, expectation and reality. It's a very complex matter, and we have today with us some of the best experts worldwide that I will introduce them later. But I would like to start with some general introduction of the topic. That's when we are speaking about artificial intelligence, we have to deal with a very different concept and definition of artificial intelligence. There's my slides here. And but I think one of the most common definition is the development of algorithms that are allowing machines to have some capability of executing cognitive task. I think Professor Rick Stevens from Chicago University and Associate Director of the National Argonne Lab will talk more about the definition and qualities. But let me say there is a very growing evidence that there is an interest around the world. If you're looking simply at the papers that are published in the last decade, you see that there is almost a logarithmic progression. And interestingly, this is matching the growth in the computing power that's it's enormously increased. And just to make some example of application of a specific task that probably this is not the true artificial intelligence, but we know that in face recognition, there are interesting applications that artificial intelligence is able to recognize details. And also this, I think, for recognition of crimes and for police. There are reports of specific application, but I don't want to spend much time on that, are showing that the computer might help in some specific function. Not sure if this is the true artificial intelligence because they are very specific, but in this specific task, the computer is performing much better. For example, X-ray, interpretation of X-ray, there is already scientific evidence that in thousands of images, artificial intelligence is able to do better than the performance of radiologists. And that is not surprising. And this is why I'm suggesting some of our students be careful in choosing that kind of specialty because it probably will disappear with time. And also other, I will stop here because, I think there are huge perspectives and in healthcare, and we will learn more at the end of this webinar. And in particular, I think in surgery, in preoperative, intraoperative, postoperative, in general organization, that there are a huge perspective. So I would like to, I respected my time, and I would like to ask Professor Rick Stevens, that is a professor of computer science at Chicago University and associate director of the National Argonne Lab, one of the most prestigious institution in the United States, and probably they are the most powerful computing system of the world at the moment. Please, Rick.
Okay, thanks, Peter. So let me, I have about, I don't know, 10 minutes or so to talk about this first part, which is a kind of a short and long-term perspective on AI, sort of what's happened and where are we going. So our three things have actually driven AI progress in the last probably 10 years. One is that there was about 50 years worth of academic work that created a whole body of methods across the many parts of AI, which I'm not going to talk about, which prior to about 10 years ago were really disparate areas. So computer vision was separate from language processing and so forth. Many methods had accumulated, but very little kind of success had happened. But starting about 10 years ago, several things changed. One was that we started having the ability to have very large data sets. In particular, there were data sets built that were for benchmark problems in computer vision and text understanding, and I'll talk more about one in a second. So big data sets became possible to accumulate them. The community started curating them, made them available, and created challenge problems for the community to practice on. Okay, so that was part number two. Part number three is that computing became much more affordable. So we learned in the earlier little introduction that there was this massive increase in the amount of computing, but what's really driving that is affordable high-performance computing has become kind of ubiquitous. So this idea of GPUs that originally were developed for graphics can be also used to train deep learning models in particular, and they're everywhere. Everybody has access to them, students have access to them, big supercomputers are building out of them.
Can you put in full screen mode your presentation?
Oh, sure, give it a try here. Okay.
Sorry.
No problem. Okay, so let's go back to the data for a second. So probably the most famous data set that has existed to drive AI progress is called ImageNet. It was created by Fei-Fei Li back in 2009. Her colleagues thought she was crazy. At that point, the idea of building a data set with millions of images and labeling them was considered impossible, just from the sheer amount of effort. But she figured out how to use the Mechanical Turk, which is a service that Amazon offers for you to create little mini work tasks that get farmed out across the world for pennies on a task. And that process enabled her to label millions and millions of images relatively inexpensively. In fact, this project was at the time, at the height of its work, was the #1 user of that service. Had probably thousands of people around the world helping to label these images. Of course, a lot of the labeling was initially done by graduate students. So this database was not just a random set of images. It was a set of images that were carefully chosen to represent another database that existed called WordNet, which was a database used for training natural language processing systems. And what they wanted to do was to create an analog in the visual space that mapped onto that text space. Now, the reason I'm focusing on this is that in order to make progress in AI and in the kind of powerful AI that Pierre is interested in, okay, we need to create benchmark problems and the training data at scale for training AI to do robotics and to do surgical robotics. And there was not yet a plan to do that. So ImageNet was critical, this idea of a large database that is beyond state of the art, that requires growth in the methods in order to advance the problem, is absolutely critical. Now, there's been a huge progress in the particularly since 2012 on deep learning in particular, And I won't go through these in detail, but you've seen some examples, but image classification, whether it's in medical images or whether it's in just general images, has essentially become nearly a solved problem with AI. Speech recognition, handwriting recognition, you no longer worry about writing by hand if you're sending a letter or something, it can just happen. Of course, people don't send letters anymore. Translation, text to speech, you have digital assistants, all this stuff. So this is all happening. Probably the thing that is probably more shocking to people is that AI is starting to solve problems in science. For example, on the right here, Google DeepMind has a couple of years ago basically essentially aced the protein folding problem. And this was a shock because the community's been working on this problem for many, many decades and was making very, very slow progress. And by using deep learning methods and training on, again, a very large amount of protein structure data, they made progress on this problem. So as was said earlier, I mean, there's been a lot of discussion and some speculation about how AI will impact medicine. And I last fall I taught I've been teaching many courses on AI in medicine, and of course there was a nice review paper which you could look at, but it basically summarizes that across many specialties in medicine, there is progress being made on using machine learning and AI, and we use AI kind of as a loose term to include machine learning. And when people say AI, typically they want to talk about something like an artificial general intelligence as something that is doing more than just applying a machine learning algorithm. But often these successful results are actually coming from relatively simple machine learning methods just applied to large amounts of data. If you look on the right-hand side, right panel here, under the second column where it has N, this is talking about how many samples are used in the training set for these particular problems. And many of these cases have over 100,000 training samples. And these are the typical results that we see also in our work, where if you have 100,000 or more samples, you can get models that have pretty high R-squared values and so on. And so large amounts of data is generally very, very helpful. As was also said earlier, there are starting to become an increasingly large list of systems that are outperforming medical experts in specific domains, what we would call narrow AI, ranging from imaging, largely based on imaging, but also in some cases of combining, say, observations and lab results for diagnosis in particular. Now, if we want to look long-term, and I think I'll be done here in a second, and then there's many talks, and I think we come back a little bit later. Let me just lay out what I think the long-term prospects are. If we have enough data, whether it's real-world data or data from simulations, I believe we will essentially be able to build some kind of AI system, whether it's a machine learning based system or deep learning system or reinforcement learning system or something in that direction that can solve essentially most problems. We're starting to see, and there's this overwhelming trend that this is the case. So data is critical, and if you have enough of it, a problem essentially will be solvable. Number two is the kind of problem that robotic surgery is actually in this very difficult class. It's not in the class of anything that we've been talking about earlier. It's a time-dependent, multimodal problem. Okay, it happens over time. You have input data that's images, video, force feedback. You're dealing with a soft material that deforms. It's got many complications. All right, so in order to actually build systems that can work on that, we're going to need to have training data and simulators that integrate that type of data into a playground. We call them gyms, actually, in the AI research community, that integrates all of that so people can play with ideas in that space. Without that environment and without massive amounts of data in this form, we can't make progress very quickly. The third point is that there's a general notion that's happening. I mean, we think of self-driving cars as a very commonly understood paradigm. That is, you've got some task, a human currently does it, they do it pretty well. We're trying to automate it because it frees up the human to do some higher level processing or to supervise or to sleep or whatever they want to do. And the question is all the investment being made, say, for self-driving cars, can we leverage that somehow? And I would say the answer is yes. It's a reasonable conceptual paradigm for what we want to do. It has multimodal input. It has complex controls. It has, of course, a life and death situation kind of wrapped around it. It's a safety thing as well. But of course, there's many details that are different. But in order for robotic surgery to advance, we have to find a way to leverage that. There are billions of dollars going into the AI components of self-driving cars. And in the short term, there will never be that much money going into the robotic surgery R&D investment. And so we have to find a way to leverage that. And I'll stop right there, let the program keep going, and we'll come back later and I keep going. Thanks.
Thank you, Rick. I think it's fascinating. It's the perspective are wonderful. I think we will do a first set of presentation, then we will come back with questions, and there are tons of questions that I would like to make you. So I think the second speaker, we will see something more specific. This was a wide definition of perspectives and of artificial intelligence, some specific applications with the intraoperative imaging. And Professor Leo Chen, that is a research professor at University of Illinois and director of our research robotic lab. And so I will ask Leo to give his contribution.
All right, can you see me? Okay, all right. Thanks, Dr. Gurnalagi. So my name is Leo Chen. I'm from the UIC surgery department. It's an honor to be here. You know, I'm not a surgeon, so I will give this presentation from a bench research perspective. Okay. So as I said, I'm from the Surgical Innovation and Training Laboratory. So this is actually a new laboratory established by Dr. Giulianati, Dr. Benedetti in the surgery department, as well as the colleagues in the neuron surgery department. We are actually almost at the end of the construction phase. So the new lab will be operated in the middle of September. So here is a few snapshots of the new lab. We are very excited about the new lab, and we certainly looking forward to collaboration with the communities in the surgery community there. So stay tuned. There are more will come up. Okay. So the one thing actually stand out. We believe that one thing that we stand out different from other training center is that in our training center there, the research is a very, very important component there. In fact, it's one of the three major components in the new laboratory. So this slide highlights the research component, research activities in our lab. So we have both clinical research in the field of simulation, planning, and then procedure and itself, as well as benchtop research and focused on the theme of quantitatively surgery. So what we like to do is we want to quantify all perspective of the the surgery, and then things include the hands movement, that's include both inside the patient body and also outside the patient body, and then what exact tissue response and the tissue status during the different procedure, under the different maneuver of the instrument, as well as the imaging component, how to overcome the imaging, the depth, the optical imaging depth, the depth of optical imaging is not deep enough. And as well as another major area we focus on is the intraoperative molecular imaging. So, so today's topic, I will mainly focus on this area here. And then, of course, with all this data here, we will hope that we will develop a system can be either the context awareness to be a surgical assistance system for the surgeons, as well as some, eventually leading to the system Rick just talked about, the surgical automation there. And the things in the red actually highlight the infrastructure or the instrument we have in the new lab to be able to implement the research effort. So let's go back to the intraoperative molecular imaging. So this slide really highlight where the position of the molecular imaging in terms of in the robotic surgery, right? If you look at robotic surgery, there are three pillars, right? Basically, we have surgeons, we have a robot, and then the visualization. So this actually the three key components there. Those three key components has to be all in the best conditions in order to enable a perfect surgery, right? You can't just miss any one of this component there. If you look at the, if I focus on the visualization there are basically two types of imaging, right? One is preoperative, the other one is intraoperative, right? I mean, for the intraoperative and the optical imaging certainly play an important role there because, it's just you need a constant imaging there. You just cannot input too much energy, things like X-ray or stronger magnetic field, even radioisotopes in there. So optical imaging will be the key imaging modalities for the intraoperative visualization there. And the traditional, of course, up to now, that's the imaging mainly is from the surface. It's a bright field imaging mainly for surface to visualize the surface of morphology and structure. But this have a certain limitation there, where the surgeon cannot see where the vital organs look underneath the surface, and of course, there's no way to directly margining what's the lesions, what the tumor mass there. So that's why the molecular imaging can come in there. So basically, that's enable the surgeon can see the tissue at the molecular levels, right? Based on this one here, there are two types of imaging, molecular imaging. One is based on the intrinsic property of the image, the tissues. In other words, tumor tissues have their different intrinsic property compared to the normal tissue there. You can develop imaging modality based on this difference between these two properties there. And of course, there's another major effort that using a target specific probe to realize the molecular imaging, right? So I will give if you look at the AIs, all this area here, the AI has been pretty important rules. People recognize the potential power of AI. So if you look at literature there are tons of study on the AI for assisted the CT MRI, this preoperative imaging, and of course the AR insisted is it is a traditional imaging there. But the AR assisted molecular imaging is a relatively new thing there. It actually just come out very recently, and I like to give you highlight two of the most important. I believe in the new imaging modalities, compared to conventional modality we use, which is a fluorescent one. The first one is this Raman imaging. So this is actually the new papers come out just last I think earlier this year. So basically, using the Raman imagings and combined with the AIs to recognize the tissues. So basically, it's on-site pathology approach. So what due to time, I can't go through the details of Raman imaging. So basically, it takes advantage that tumor tissue have a high lipid protein ratios than a normal tissue there. So by characterize the ratio of the lipid versus tumor there, then you actually capture the difference in their Raman signature there and then build the imaging. And then you can apply the AI technology, the deep learning methodology to actually, again, to recognize and those imaging there, and then you actually can quickly identify what's the tissues there. So you can see here, this is actually the program, and you can see here, actually the entire process can take about less than 3 minutes there, compared to conventional pathology, which takes about at least 3.5 hours there. So it's a significantly advanced in terms of the, that's why it's a near real time, right? So it's like it's more like an intra-optical room pathology, this type of approach there. The second imaging modalities I want to people to pay attention is the photoacoustic imaging. This one here take advantage that when you have the dye molecules actually can absorb the absorb the light there, then they actually can emit the acoustic waves to the surrounding air, which can pick up by any detector there, the ultrasound detector array there, and then you can form imaging of the tissue there. So here's the example. Here you can see that once you inject a antibody specific to the tumor area there, and then you apply the acoustic imaging there, you will see. I just move here. Yeah, you will see that this is actually the imaging probe there, imaging, and this is the photoacoustic imaging. You can see have a better contour and the better sharper imaging compared to the fluorescent imaging. And more importantly, is overcome the depth issues. Normally fluorescence imaging, the photo, bright field imaging there, we talk about a few millimeters of depth penetration there. But once we have the photoacoustic there, now we actually expand to a centimeter depth of imaging there. So that's give the certain significant power. If you look at this two imaging modality there, you realize that those one all did it in the X wavelength, in the sense that they normally have to take the tissue out and then do the imaging there. The reason for this one is that if we want to do this intraoperatively, you have to make sure that the surrounding areas, no fluorescence or no signal there. But you cannot do this one because the probe will have the fluorescence, have the Raman signal at all the time, right? You will see the normal tissue also have this fluorescent signals during or Raman signal during the initial injection of the probe there. So that's why our focus there. So our approach in this one here is that we like to develop an activable, which means that it can be turned on only show fluorescence or Raman signature or any type of signals only in the tumor areas, not in the normal tissue area. So what we're doing here is that we're actually using this dye quenching complex there, and then due to the tumor specific in situ, either metabolism or the enzymatic interaction there, we can actually remove the quenchers from the complex there to resume the fluorescence. And I'll give you a very example here. Is that that's the initial study we have. You can see this is actually a uterine cancer model there. You can see there are tumor mass here, and then we use this side as a normal tissue as a control side. We actually apply this complex, this dye quencher complex to the tumors, actually a topical approach. And then you can see after 24 hours, you can see the tumors actually light up very nicely. And then the control area actually didn't see any there. And then of course, after 48 hours, everything gone. But this is not good enough for intraoperatively, because in operatively, you're not wait for 24 hours, right? You want to see it like in a couple minutes here. So that's exactly we actually modified our probe there. So this is actually temporal imaging of a series of the imaging of the mouse after the injection of the complex molecule there. And now you can see there after 2 minutes there. Now you can see in the tumor mass there you see fluorescence now, and then but in the control normal area there you don't see anything now. Now up to 15 minutes there, then you start to see your normal tissue area also light up. Of course, after 100 minutes there, both sides light up, and then after 24 hours, for reasons that we still try to understand that the dye still maintains actually in the tumor area while in the normal area is disappeared, right? So this is actually the original observation we have, and then of course after 4 days everything's gone, right? So the initial results suggest that our probe it can be used for both short windows and long-term windows. So the fact that in 2 minutes it will show up the contrast between the tumor mass versus normal actually is promising. That means we actually can monitor the tumor mass or margin tumor mass intraoperatively. Right? So that's give the power of the imaging probe that you can actually specifically imaging the tumor area there. We probably just inject this one here, skip that one. So I mean the perspective of this one here, if you look at the AI pipeline for the drug development, there is already established the AI for drug development. I think the RICs also have a research effort there for AI for drug development there. All the big pharmaceutical companies there, they all have this well-established AI for drug development. What I believe that we actually can take advantage of all these pipelines there, and using those same pipeline to develop the imaging probe. Because if you look at the imaging probe versus the drug, there is not much different. The drug is actually a binding target, and then there is some action there, right? But for imaging probe, we only care about the binding side. So in a sense, it's actually easier compared to a new drug development. So I believe that if we can put more efforts, by putting more efforts on the similar approach as the AI for drug development, we should be able to get more an imaging-based probes for this one here. With that, I think my time's up, and I will stop here. Okay, thank you very much.
Thank you, Leo. It's very interesting, and I do believe that Rick Stevens is interested in this application, and we do hope that we will be able to do some research project on this specific task that is, I think, is very, very interesting. And we will discuss more about that. But now we would like to know from Professor Mehran Anvari. Professor, I think it doesn't require introduction as a full professor of surgery at McMaster University in Canada, Ontario, and is one of the pioneers of robotic surgery worldwide, and is involved in hundreds of research with NASA and with other institutions. Is a celebrity. So I would like, Mehran, what's your opinion? Which are the current applications of artificial intelligence in the medical field, and in particular in the surgical specialty?
Thank you very much, Piero. Can you see my screen?
Yes, we do.
Okay, well, as was mentioned by Professor Stevens and Chan, the artificial intelligence brings to us a number of important capabilities which probably will outstrip our human brain. While we still are better at abstract thinking, common sense, ethics and morality and compassion, machines probably can do a better job of pattern identification, eliminating bias. And now with the machine learning, they can really infinitely learn from each operation and and really provide endless capacity. As was mentioned, the research in the field of AI is not new. It was 1997 when some excitement was created when IBM Deep Blue, which is the precursor of Watson, beat Garry Kasparov, then the world champion in chess. And really, we've seen in the last 2 decades increasing application of some degree of autonomy, not necessarily always full autonomy, in various areas. In fact, in medicine, over the last, I would say, 10 years, we are seeing increasing applications of AI in various fields. And already we are having evidence that in many fields, AI is outperforming human diagnosis and interactions with the patient. As was mentioned by Piero, radiology is obviously a clear area because it is very much based on pattern recognition, but there are other fields, neurology, critical care, and even surgery in some aspects of image-guided interventions where really seeing application of AI may actually show benefit. And then there are other areas, cardiology, oncology, ophthalmology, where it is emerging as a potential area. Radiology, ChestNet a few years ago showed that was much more capable than a 4-expert radiologist diagnosing pneumo and other lung pathology. And more recently, we have seen a number of important articles in very excellent journals, including New England Journal and Lancet, which have really shown, and in certain pattern things such as diagnosis of breast cancer, prostate cancer, that AI can outperform expert radiologists in detection and diagnosis of these tumors. And I think this is an area which is going to grow, and there already are a couple of platforms by Google AI and IBM Watson, which is being made commercial, which will assist radiologists in diagnosis of these early cancers. In neurology, we now have very simple AI platforms using your mobile devices, which can assist in the diagnosis of autism spectrum disorders, which is often parents wait 1 to 3 years, and now with simple tools like what is being offered by Cogna, can actually make that diagnosis very quickly and actually initiate treatment. Another area which is now seeing an increasing use of AI is in diagnosis of Alzheimer's, because it can bring together not only images from MRI, but also their mental state examination. And again, the new platforms is outperforming neurologists in identifying and diagnosing Alzheimer's, which I think is an important tool in this area. In critical care, I think if you go to ICU, you will see increasing applications of AI, not just in CarePath, but also there are a number of systems which can look at adjusting the airflow and various ventilator support that patients require during weaning, and be able to adjust this on an autonomous mode and really make that your life a lot easier, as well as IV infusion, making sure you are maintaining adequate flow of volume to titrate. And again, these are simple platforms, but are making your life in ICU a lot easier. In oncology and tumor detection, I think there was a mention by Dr. Chan, so I won't go, but it's really AI for genome diagnostic, can look at identifying mutations with high accuracy. And I think at the moment hasn't gone far enough to offer treatment advice, but you can imagine that it won't be long before you actually can do an AI evaluation of a tumor and actually look at what are the best treatment options you can offer your patients with various cancers. Prostate cancer is another area which I think in diagnosis of lesions and being able to decide on the best course of management of these cancers, you are seeing AI platforms being offered, which are going to make a big difference. The beauty of AI is that it doesn't rely on just one data point. It can bring multiple data points. So it's not just one MRI, or you can look at perfusion. So it can bring all the various, and including pathology and histology, and really base its diagnosis and its care path and its recommendation on multiple data points. Skin cancer is very simple because I think again, it's mainly pattern recognition, and you can see there are currently platforms which can outperform dermatologists in detecting malignant melanoma. So really, you are seeing increasing applications of AI already in various fields of medicine, which are making a difference. In cardiology, and again, evaluation of echocardiograms, and now the researchers have achieved successful classifications of various cardiac malfunctions and using echocardiogram. And again, this is going to really revolutionize the field of cardiology. Heart attacks and stroke, there's a system which has been developed in UK, which compared to conventional methods can actually make a better diagnosis for heart attack and stroke in the next years. More of a prognostic AI, which is a very important form, because I'm working with a group which are preparing astronauts for the Mars mission, and they're relying on now use of AI in pre-diagnosis. So before a disease state is produced, can the AI predict evolution into a disease, and can you actually instigate changes to prevent disease actually occurring? So before pre-diagnostic use of AI. In the area of surgical robotics, we've already heard 2 talks on this. This looks as if it's going to be a evolutionary path of surgical robotic. The current systems that we're all using, the master-slave systems, which are still going to be here to come, we are now seeing increasing number of automated robots with some task specificity, and now moving slowly towards autonomous system with adaptive learning, capable of learning from each of their procedure and being able to think and decide. Clearly, that level of autonomy it is still the next frontier. As you can see, there are multiple levels of autonomy. Currently, we are working with Da Vinci's, which is basically zero, no autonomy. It's basically master-slave. And we now have systems which have some robot systems, some task autonomy. And then we're really moving towards a high autonomy where the robot is capable of making decisions, and then full autonomy where really no humans need to be in the loop. Again, we have seen some examples of these surgical robots reach us. At the level 1, we have Acrobat from Sweden, which is some capability of some minor task or decision task oriented autonomy, same as the STAR system. And then the new intracardiac autonomous catheter navigation has some condition autonomy, but really the high autonomy and full autonomy is still the next frontier. This is the STAR system, and it was developed by Children's National Health System in Washington, and AI power system that uses lightweight robotic arm to sort of place a line of specialized sutures by itself. So the autonomous or some degree of automated autonomous suturing capability. What is, as Professor Stephen mentioned, what is really exciting about the next level of autonomy in robotic is the whole notion of machine learning, that the robot can actually learn from each of its own interaction and become better at operating on a case by case, which is really more than what we can say. Yes, we gain experience, but it's tough to say we are getting so much better each case we do. And we tend to plateau and then sort of decline towards the latter part of our surgical life. The autonomous robots have intelligence-based learning, which allow it to perceive and respond to environment and improve. Some of the early candidates are obviously image-guided detection and biopsy ablation of suspicious lesions, things like in breast disease, liver cancers, kidney, prostate. And there are now some platforms being developed, which is allowing systems to be able to detect and biopsy and potentially ablate lesions in one setting in these circumstances, which really make a big difference. The Mako system, which is offered by Stryker for knee arthroplasty, I think the next iteration, they are looking at some degree of at least level 3 or 4 autonomy to be able to do some aspect of the knee replacement in a partial, semi-autonomous way to overcome some of the manual dexterity issues that sometimes may haunt surgeons. And again, there are now simple systems under development for emergency care, such as diagnosis and treatment of tension pneumothorax in various ambulances, etc. So we do have a number of systems, but as Professor Stevens says, the big issue is the money required to invest in these areas to develop that to the next level. And one of the beauties is that there is investments being made because we have, as a society, decided the journey to Mars is the next frontier. And I certainly, my own involvement, as Piero said, in looking at exploration of telesurgery in very extreme environment. I've been involved with both NASA and CSA in looking at this. And we really, very early on, it was obvious that for any long space travel, such as Mars, where you have a time delay of 70 to 40 minutes, the routine telesurgery, even some degree of assisted autonomy is not going to do. And so you really are looking at developing systems which can function in a pretty close to 4 or 5 autonomy at these long journeys. You can't wait for some degree of human supervision to be able to perform various tasks. Now, the beauty is that you're dealing with a dozen or so potential simple surgical things that you need to offer. And there you are seeing some investment. My own government has invested $2 billion for some degree of robotic autonomy for the next moon lunar gateway, which is going to start being built soon, and about $10 billion for the Mars mission, hoping to provide that as its own contribution. And as part of my work, we recently did a proof of principle to show that we are capable of connecting the IBM Watson to our image-guided automated system to make an autonomous system which can actually detect a lesion, plan and execute a simple surgical maneuver without a need for a human in the loop. And this success led us now to working on a very simple systems for a number of things, such as treatment of pneumothorax, drainage of abscesses, dealing with kidney stones, etc. So we are now embarking on the next phase of building something to some degree of level 4, level 5 autonomy. My own thing is that future of robotic surgery, we are going to see incorporation of artificial intelligence into surgical simulation and surgical procedures, as was mentioned. I do think in certain areas, surgical robots will surpass humans in their ability to function. And I don't believe it will entirely replace human surgeons. However, they will assist to improve the outcomes. And so our role as surgeons may change a slight, but it's not something to be really be fearful. I will talk a little bit later about some of the challenges, obviously, to this expansion of AI in the field of surgery, but I'll stop at this moment.
Ameren, fantastic. Congratulations, concise and clear. And not only you gave an overall overview of the present, but I think you open up some future perspective that are really very fascinating. But this is what the surgical community is doing, is thinking. We would like to know the perspective. One of the main actors is the company Intuitive that developed the most successful robotic system that we have been working clinically in the last 20 years. So we invited Intuitive and Anthony Jark, that is the director of data and analytics at Intuitive, is with us today. And so we would like to know from him, which is the perspective of the company in this field.
Great. Thank you, Dr. Giulianati, for the great introduction, and thanks for the great perspective from the three previous speakers here. I think we can try to put a slightly different viewpoint on this from Intuitive's perspective, and on a topic that my team and I at Intuitive think a lot about, and we'll speak specifically about surgery, not broader within AI, but I'll work to try to define what it is from our perspective and how it can contribute to making surgery better. I think many of us touched on this earlier, and we showed many technologies that could potentially impact surgery. But I think it's important for us first to kind of step back and say, why are we deploying these technologies? Why are we trying to use these in surgery? And that boils down to what problem are we trying to solve? And I think Dr. Chen mentioned exactly this, which is how can we make surgery better? There is extensive evidence showing that complication rates, readmission rates, many factors still remain a huge challenge. And so how do we chip away at these things to make surgery better? In particular, is there an optimal way to perform surgery? And if there is, how can we teach it and scale it in order to enable the mastery of surgery? And I think many of us here in this whole community are trying to solve this problem. And we've been at it for a long time at Intuitive. And it's really, really hard. We're seeing that kind of echo through all these presentations here. It involves lots of factors. And here's one approach that we think it takes to kind of actually deliver solutions in this space. And that's through technical, clinical, and operational mastery. So technical mastery, how do we use things that we've seen today, like robotics, imaging, computing, and analytics to get better as a surgeon or to perform the surgery better? How do we develop systems for clinical mastery to achieve the right outcomes? and then operational mastery, which matters a lot. And that's how do we perfect workflows and achieve the right economics so that hospitals and health systems can actually use these capabilities. And it really, I think all of that is to touch on these 4 elements of the quadruple aim, which is improved outcomes, patient experience, care team experience, and total cost to treat. And if we look at this, we really see that surgical AI, which might fall into the technical mastery component, is really one element that gets us to that end solution. And it's going to be a really multidisciplinary problem for us all to get there. And you know, kind of following that logic, technology, like we've talked about and is the focus of this seminar, is incredibly important in enabling. But I think you know, healthcare is really fundamentally about people. And so we need to deeply understand who's using it, what it's used for, and the environment it's used in, so that we can come up with the right solution for that specific problem. And so now that we're kind of aligned to why we're really excited by surgical AI or AI more broadly, and why we're excited by other technologies, let's dive into how we define surgical AI and what we think it can do, especially given there's quite a bit of hype around this, and I think it's important to kind of ground it in some interesting examples. So I think we've heard this throughout, but I think this is the definition that I'd like to present, which is surgical AI consists of computer systems that can augment human capabilities using specialized algorithms developed from clinically representative data. And really, I think you know, there's this debate and discussion, but I'd like to emphasize its ability to augment, right? Humans have strengths, technology has strengths. And what can it do? Surgical AI fits into decision support systems in our mind. And those decision support systems deliver optimal information at the optimal time with the optimal tools in support of that initial goal of how do we make surgery better. And surgical AI is really joining a whole list of other technologies, right? It's not standing by itself, it's joining many others. And I would argue that some of these technologies remain very disconnected. And so I think it's the responsibility of us as a community and us as Intuitive to try to organize these technologies so that we don't complicate things, we really make things better in surgery. And I actually think surgical AI plays a critical role in this, given it speaks information, it speaks processes like we saw in some of the previous presentations. So let's see how this might happen. First, how do we extract the optimal information from surgery? This was touched on a few times, but I think that there's really an opportunity by placing a computer between a surgeon and a patient to capture really meaningful information about a procedure. And we can use this information to recognize patterns that would potentially allow us to bring that enhanced precision and guidance to surgery. And we can use advanced analytics potentially even on top of that to identify performance features that might align with current state of the art in terms of expert evaluations, but try to remove the subjectivity that's innately human and then that machines are pretty good at. But this is a hard problem. And so the question is, how do we know which metrics actually provide objective performance indicators in surgery? Does operative time allow a surgeon to know where she is kind of along a learning curve? Or are there other factors at play? What about the number of surgeries that a surgeon performs? If you perform a certain number of surgeries, does that necessarily mean you have better outcomes? Or do we have to dive deeper? And one way to dive deeper might be to look at critical steps of surgery and then task-based objective performance indicators to characterize those critical steps. And we're not going to touch on it here, but there's been some really exciting work in surgical AI that has looked at identifying and extracting these metrics from surgery. And I think that's going to provide some really exciting research and directions in the near future. But it's also important to deliver that information at the optimal time for each problem we're trying to solve. And in many situations, delivering the information at the right time requires situational awareness. One example of situational awareness could be to recognize the underlying activities or steps within a surgery. And machine learning algorithms have shown incredible promise to be able to do this, to be able to recognize these patterns so that we can then deliver information with the right context anchored in clinical understanding or deliver the right tools at the right time. But it really comes down to being able to deliver tools that impact surgery as well. And I'd like to walk through several examples that we have that are in the market today that are starting to do this. So the first set of examples are intraoperative guidance capabilities. And they use augmented reality to do this. On the left, we have a technology called IRIS, which is a 3D segmented imaging technology being used in a partial nephrectomy. And on the right, we have our flexible robotic catheter platform called ION being used to navigate to a lung nodule. And in both of these situations, a CT scan is segmented using surgical AI capabilities and then being incorporated into a virtual reality setting so that surgeons or pulmonologists can better see and plan. So again, we're chipping away at this problem to try to improve surgery and help the surgeon. And I think something that we didn't talk too much about today, but was kind of, I guess, implied by the fantastic training facilities that are going in at UIC is how do we improve surgical education and training by personalized learning and building out a big digital ecosystem. And I think that many of these tools that we have in this space could be built or informed by surgical AI and make a difference in the near term. And central to these tools, I think, is access so that all learners can be able to get their learning pathway very readily. And kind of cloud connectivity and integrated systems are going to be critical to that. Let's walk through each one of these. First, there's intuitive learning, which is a platform that we've built that allows surgeons to access their training pathways right at their fingertips. And it's something that we've worked with many of our customers and care team members to be able to try to develop useful training materials that can be kind of accessed from anywhere so surgeons can learn. And it includes a lot of different features. And one in particular is an interactive clinical video library that's been designed by surgeons and that enhances what's most clinically relevant. But I think what's really interesting to this and what pertains to the conversation today is the ability for us to be able to tailor learning to an individual by observing how others learn most effectively. And that's powered often by learning algorithms. Virtual reality is also an exciting capability. And here's an example of SimNow, which is our cloud-enabled simulation platform. VR has shown to be an incredibly interesting and exciting space for surgeons to develop and hone their skills outside of the OR, using gamified environments like you see on the left or very clinically relevant environments like you see on the right. And I think researching how VR practice can potentially impact intraoperative performance is going to be critical. And these identified best practices are often discovered using surgical AI technologies to decompose these data streams and this information that we can capture. But it's going to be important because we need to validate and then share this information across institutions to really improve learning, again, powered by some AI capabilities. I think another thing that was touched on by a few different speakers today was the ability to use simulation to be able to develop and test AI technologies before deploying them into the operating room so that we can do it safely and responsibly. And I think this is a very exciting area. I think one particular space that I want to touch on is how we can incorporate best practices into simulation. And so we talked about the ability to teach it and scale it to enable mastery. Let's walk through one example of how do you hold a needle in order to suture with greatest skill and efficiency. And I'd like to highlight one study that uses a data-driven method to do this. And this is by a collaborator of ours at University of Southern California, Dr. Andrew Hung. And what he did was characterize the gestures of an anastomosis during a prostatectomy using system data and video data. And what he showed is that those gestures that did not align with the common ones resulted in lower efficiency, more attempts, and more trauma. But it really hasn't been previously shown via these kind of rigorous quantitative methods. And so if we can take gestures like these and incorporate them directly into simulation, we might be able to teach the right skills. And lastly, I think there's an exciting area that the community is pursuing, which is how do we help surgeons improve through post-operative review? And I think this is critical, but very challenging and maybe a step before jumping into intraoperative guidance or to complement intraoperative guidance. And it really requires us to use the right information, such as like the system data we saw before or video data, and add the right context. So how do we extract video highlights or task-based objective performance indicators to then give surgeons tools that can identify opportunities for improvement. But identifying those opportunities is really the first step. And so this links back into that ecosystem that we mentioned before to be able to surround a surgeon with capabilities like intuitive learning, SimNow, telepresence or teleproctoring, surgeon-led courses, to really improve with greatest efficiency and ease. And again, organizing this information in this manner requires many machine learning capabilities to do it at scale. And I'll just touch on this really quickly. I think this is something that Intuitive takes very seriously, but we really want to foster innovation. So we know that it's a huge space, and so there I think are needed elements of AI research that have to be addressed. And one is open data sets. So we've been part of Endoscopic Vision Challenge for the last 4 years, where we contribute open data sets to the machine learning community to solve some interesting problems. There's one that my team is leading this year in terms of surgical visual domain adaptation. We have the Da Vinci Research Kit, which allows academic teams around the world to explore these surgical AI technologies in a lab setting using decommissioned hardware from Da Vinci Systems, which is an awesome gym or playground for some of the capabilities. And then fostering innovation that's initiated by research teams all over the world through grants on education, training, clinical and technical topics. And one thing that we talked about today briefly in all the talks is data. And that's something that Intuitive is sitting right in the middle of, and I think we take very, very seriously. And so I want to touch on 3 things here. So one is in the healthcare space, we at Intuitive and many others have to comply with lots of data privacy laws and regulations, which are really important to navigate this and to really fuel AI. Product data that we have at Intuitive is used to kind of improve the safety, reliability, and performance. And then data collection and use outside these purposes are governed by individual agreements. And I'll touch on that in the second talk today, or second conversation today. But the reason I bring this up is that conversations about surgical AI are really conversations about data. And I want to make that really clear here so that we as a community can figure out how to navigate this space as transparently and collaboratively as we can. And so to wrap up, I want to just kind of touch on a few things here. I think we've seen by the presentation today, and hopefully by some of the work that Intuitive is doing, that surgical AI is an incredibly promising field with a lot of cool capabilities, both in the near term, but also in the long term. However, it's incredibly hard. Surgery is a high stakes environment with complex decision-making, sensor motor skills, and care team coordination. And that means introduction of technology is going to be challenging. And I think it's going to require a collaborative approach to build out these tools, technologies and ecosystems that could be facilitated by surgical AI. And so how can we as a community come together to use these technologies to deliver actual meaningful impact? And what will it take? I want to touch on a few challenges that I think are important. And here are the 3 of them. First, we must focus on and validate clinically meaningful technologies, right? We don't want to just go after technology because we have a really cool capability. We want to solve something that brings real impact. Secondly, we want to develop a common vocabulary to describe surgery so that those that use our technologies can really understand them. And there's a SAGES initiative, I think it was referred to from a paper earlier, that's really spearheading this in an awesome way. And then lastly, I do think that we need to stay on top of methods that address bias proactively in surgical AI, so that we can accommodate for the diverse characteristics of different patients, different surgeons, different hospitals, different care teams around the world. I think there's a lot of bias already built into the world today, and so we're in the early stages here, so we can absolutely take action. So with that, I'd like to thank you all for allowing us to share our views and be happy to take questions in the discussion.
Thank you, Anthony. I'm so happy, very interesting presentation and comprehensive, and I'm so happy to understand that the company is not only interested in developing a better mechanical system, but there is a general perspective of interest in improving the surgical outcomes, having a better integration of function, including learning, teaching, and improving the coordination with all the activities that are around the surgical environment. I think we will go back with some questions and some debate, but I would like to know at this point from Mehran, which are the challenges that we are facing as a surgical community to take advantage more of the potentialities of artificial intelligence.
Thank you, Piero. I think this is, there were a number of things mentioned. One is the fact that our field is a complex field. So to see an increasing use of AI, it does require a significant amount of data acquisition and investment. It really is not as simple. I mean, even I've been involved in the Watson Collaborative for just the breast, and to see millions and millions of data points being collected in order to make a platform which can diagnose simple lesions on a mammogram. You can imagine in a surgical field, this is enormous amount of data required. And so there is a significant commitment that the surgical community needs to make in providing those data, which I think we just heard from Anthony, that it is required. And there is always the cost-benefit analysis, and it's sometimes very difficult to make a commercial sense for a company to say, we are going to pour this amount of, I mean, we're already seeing IBM and Google each have spent billions of dollars into their AI medical platforms. And to have that type of investment, it is very difficult. There is also this whole issue of ethics and morality, and where is a fine line between a machine deciding and performing the surgical acts, and is it capable of making certain adjustments which is required. And so most of the research involving AI have ethicists involved in that research, and certainly our own research, we have a very strong group of ethicists involved to help with this. The regulatory acceptance, and I have to commend FDA and some of the other regulatory, including CE, and they are very much engaged in developing a much easier role in looking at approving AI platforms. And so they are now fast tracking and also capable, and they would like to be involved in any AI related research early on, because they're trying to understand how can they make the transition and regulatory acceptance easier. If you require a randomized controlled trial, 10 years down the road, this is going to take years, and it's going to make that cost benefit analysis even more difficult for companies. So they are trying to respond to the regulatory requirements in improving these various platforms. Medical legally, this is obviously an issue which companies always have to struggle. As soon as you provide a platform, you take certain risk. It's interesting that, for example, in their IBM's breast platform, which can actually detect early cancers very early on, they, because of medical legal, what they did decide is that they release a platform which will diagnose normal. So they have a very high degree of success rate to say, okay, this mammogram, there is no cancer, versus using their platform to actually diagnose early cancers, which is capable of. But because of the medical legal challenge, they decided to first release the platform as a means of ensuring these x-rays are cleared by AI platform and definitely have no evidence of cancer in them. So there has changed strategy of how companies look at it. Public acceptance is another area which I think we are sort of have to keep in mind. My own experience has been, if public senses a benefit to them, they will accept it. So It's interesting to see some of the early platforms, such as I mentioned, the diagnostic platforms used in neurology. It is actually receiving quite wide acceptance by the public. So while this was a big concern, if there is a sense that this is going to make their life easier, faster, quicker, and better, I think the public acceptance. And of course, every system has some limitations, and we have to recognize there are built-in limitations with AI. There is no abstract thinking. There is no sort of moral code built into this. There is very little compassion built into the platform. And so those are things that I think we recognize as part of it. And then finally is, how would physicians react? Because again, the enormous amount of data required, it requires cooperation by physicians who may feel threatened. I was very interesting in again, radiologists, as I said, they're the biggest target right now in the medical field. And it requires their assistance in acquisition of data. And so asking physicians to cooperate in providing data is a challenge. And I think I want to wait by saying this is a statement which is recently released by the Royal College in Canada in application of AI in medicine, that just to reassure physicians that AI and emerging digital technologies will not replace a physician's presence, intuition, creativity, judgment, and compassion. So they may change our role with the application of AI, but it will not replace us in various other roles that physicians play in provision of care. So those are some of the challenges.
Thank you, Mehran, for reminding that the role of a physician is much higher than solving a complex specific task and we have to keep all in mind. But definitely, I think a good use of artificial intelligence can make us better scientists, and matching with our humanity side, probably we can become as an overall better doctor. But I would like to ask Rick at this point. There are innovative technologies that in some way they can change the game, because we think that there are so beautiful, interesting perspective, but there are limitations of that. What do you think?
Well, let me share here. I have a couple of thoughts I put together. Sorry for the transition time here. While I'm doing this, there's a saying that we're using in some of our AI for science discussions, and what we say there is that AI is not going to replace scientists, but scientists that use AI will replace scientists that don't. And maybe this is the same concept with physicians. Those that use it will replace those that don't. Of course, we always have a shortage of physicians, so
fantastic. I like very much this comment.
Go down market. All right, so one idea, and this was Mehran showed some stuff on this. It was present in Anthony's talk and others, but this is a general concept that is gaining more traction, this idea of augmented reality. Now, this is an example here that Google developed a couple years ago to put in the optical path of a pathologist the results of the AI, and the AI processes this sample in real time. So from a workflow standpoint, it does not change the physician. The pathologist does not have to do anything different. They put the slide in the microscope. This AI operates in almost real time, 10 frames per second, and it's essentially drawing on over the histology images its diagnosis or its augmentation. So this concept of doing two things: one is inserting into the workflow in a very transparent fashion, processing in real time, and processing that adds value. Now, I know that the intuitive talk, showed some examples of this kind of AR or being applied kind of in the workflow, but I think this is a big opportunity. It's going to get a huge boost in the next couple of years as Apple releases their, I don't know what they're going to call them, eyeglasses or something, but these are going to be glasses that look like our normal glasses, and they have processing in them, and they will have augmented VR, augmented reality capabilities to overlay on the visual field. So this will become a general capability in the population. Of course, physicians will maybe have this as well for putting patient data and patient-specific things. But in the context of robotic surgery, I think this could be super powerful to push in a direction like this. Another direction that I think is making huge progress in AI, and the issue is whether this can be leveraged in AI for surgery, is the idea of generative models and style transfer. So generative models essentially learn how to generate synthetic images or synthetic data sets from training on large volumes of data and using various methods, including adversarial methods. And style transfer is this idea of mode translation. So a simple way to think about this is those of us who are old enough to remember this, is the colorization of movies, which was done manually for a long time. And nowadays, of course, you can do it automatically, and some of the award-winning films now are done this way. But you can train essentially in one mode, either with pairs or with pair-free methods, and then translate. So this is something that I think in medical education is also quite possible here. So, there's a fine art of medical illustration that is different from just medical imaging, right? So medical imaging essentially tries to reflect the reality of the data, whereas medical illustration or scientific illustration, in fact, a cartoon that highlights what's important. And this ability to go from the raw data to something that augments with what's important, I think, is another strategy here. And this could be super useful both in training and possibly application in robotic surgery. There's all kinds of fun things you can do with it as well. We've been experimenting with it in medical imaging translation. So one of the challenges in brain imaging, and whether it's traumatic brain injury or whether it's cancer, is that globally there isn't enough MRI machines, but there are a lot more CT scanners. But many of the AI methods want to operate on MRI data. And so we took as this challenge, could we take CT data, use the style transfer, essentially modulate it to behave like MRI data, and then use the downstream post-processing? And it turns out that apparently you can do that. And it kind of works, but this is an idea that I think might be useful for going from different imaging modalities. The final example, and this is a kind of mind-bending example. So there's a number of groups in California and Japan and others that are attempting to essentially build a system that can interpret, in this particular case, fMRI data. And of course, they have strong priors here, but to translate this into a visual representation of what the current brain activity represents. And the way they do this is they put patients or volunteers into fMRI. They show them images. They capture the fMRI data. They then train a network on that data, and then later we'll show the patient a picture, or in the more extreme case, just ask them to remember the image and see if they can actually detect what it is. And the reason I'm showing this is that this is, of course, there's strong priors here, but I think in the context of surgery, if you have enough data, you actually also have very strong priors, because you have, in some sense, the many right ways to do something, and perhaps, of course, many ways to do it wrong, but maybe the signal is actually in the right way to do it. But when you look at this, on the left is, of course, the image being presented to the volunteer, and on the right is the interpretation of the fMRI signal as an image. And fMRI is quite noisy, of course, and it's low resolution. And since it's metabolic, it takes a little while for it to settle down. But you can get a sense here of having this kind of low rank data and being able to extract images from it. Now, I've been thinking about, this is a pretty powerful idea. Are there things you could do with this in the context of the surgical environment, right? Not that it's easy to put surgeons inside an fMRI machine, but there are a number of companies that are building what amounts to hats that you can wear that are monitoring electrical signals that you can get from the brain and use that data. And this could also be a data source in understanding how people are using these systems, both from a standpoint of stress, from a standpoint of focus, from a standpoint of is the brain, focus and concentration, how critical is that to actually a good surgical outcome, but also how to get people to be more focused when they're doing things and what influences that focus. So these are just random ideas. I think I had summarized this from a talk I gave last year as far as my sense of what the 4 challenges are from an AI perspective into this problem, right? So the first one is, while I appreciate that there are companies collecting data, the data is woefully not large enough nor widely enough available. These challenges, of course, are helping, but there needs to be a lot more data collection and systematic annotation of that. I think generative models have a big opportunity for making a universe of virtual patients to take that training data and produce even more potential training data by using the synthetic data. Style transfer as an abstract concept can be applied in many, many ways, but one idea is to use it to transfer the motion and operational skills from skilled surgeons to less skilled or less practiced surgeons. So in fact, act as an actual mediator. And the third thing is really making progress on large-scale reinforcement learning, where you're actually trying to get the system to do a higher level task. And this comes, of course, from progress in games, but reinforcement learning is probably one of the methods that will yield some dramatic progress in this space, and it's an area that we need to work on. So I'll leave it at
that. I think very fascinating. Can I make a question? Because one of the problems that we are facing during surgery is the integration of images with energies like ultrasound generators of energies, like ultrasound or X-ray. And it's very fascinating, the idea of a supercomputing system that is able to reconstruct the images without utilization of scans or energies. For example, based on deformation lines in the tissues, and while the surgeon is doing his mechanical work, the artificial intelligence able to calculate the deformation of tissues and make a reconstruction of the images without utilization of scans. Is this doable in your opinion? What do you think?
I think it's doable. Again, I think there's different ways to approach it. The traditional approach to doing 2D or 3D image deformation involves having some data and then putting a mesh over it and then deforming the mesh to come up with the interpolator function and then applying that, right? And the problem with that is it requires this meshing step. I think it's possible because of the progress that's been made in things like style transfer and some of these more just pure AI methods, is to make that step essentially implicit in the model, what the model learns. I know that this is happening in the context of film, so where you have actors that will say play in front of a blue screen or something, and then you have animated characters, and that mapping is done essentially without this meshing step by using AI to do it. So I think it certainly is possible that it could be done. What we need is just a bunch of data. I mean, we need to have the different imaging modalities. And the key thing about this GAN effort that's, I think, really amazing is you don't have to have pairs. So you don't have to have the same object that's been imaged in the same modalities. What you have to have is the ability to go in and out of the translated domain and then back. So you can nest these translation functions in a way that you say that you've got, say, X-ray, and you've got some surface imaging, and you've got some, whatever labeled image or whatever. And what you do is you define mathematically what the forward and inverse functions are. Again, you just learn those functions, and then you can train on non-paired data. That is proven to be very effective, and I think it could be done in medicine. Again, it's just we need a systematic strategy of collecting the data, organizing it, and then challenge problems are a good way to motivate the computer scientists who otherwise aren't interested in medicine, but having very clean problems that they can then play with. You have lots of people doing things, and then you harvest the best results and then translate it back into the medical space. So I think it's very doable.
Thank you. Anthony, we learned that it's crucial that we are able to collect mass data. And what's the opinion of the company and in this particular point?
Yeah, absolutely. Let me go ahead and share my screen here. All right. So I think that what I'd like to do is talk about data and data that can kind of make measurable and impactful change to healthcare systems. The topic was kind of mass data at the hospital level. And I think kind of to the point that was made before is that many hospitals are starting to standardize, at least within robotic surgery, which is a cloud-connected integrated system, because they're now in these later phases, right? They're not in the early phase. Not all hospitals are in the early phase of adoption. That they're now operationalizing and kind of standardizing their practices to try to bring value, and that's because it's becoming more commonly used. But then puts responsibility on companies like Intuitive to make sure that the use of those systems are effective and efficient. And so I wanted to walk through how we look at this from a very high level perspective. We can dive into details and questions afterwards. So this lays out the fact that data has been collected and papers have been published extensively to try to change or identify differences in performance and efficiency across modalities of surgery. There have been thousands of publications on Da Vinci systems in general. However, I believe that these studies are often single center studies, and that rarely changes behaviors, whether it be because randomized controlled trials are very rare, or they don't necessarily predict the same outcomes as all hospitals. Like not all hospitals are exactly the same, not all surgeons are exactly the same in how they deliver care. And then it's about other factors like workflow, economics, and standards. So we're seeing this challenging problem emerge. And so if we go over to the right where it's hospital, up until this point, it seems like hospitals and surgeons have had to rely on comparative studies to kind of change their behavior, which is other people's experience. And so the approach that we've been taking is that we've been trying to work with hospitals to be able to measure things about their systems and help them understand their processes based on KPIs that matter to them. And I think that's actually worked quite well to bring change and improvement to surgery now, not longer term, but now across many hospital systems. So let me walk through an example of what I mean by this, because maybe it'll provide context. So if we look at integrating data sets such as health system data, EHRs, and then robot data like Da Vinci produces, things can get really powerful. So we're going to start high level and dive in a little bit deeper. So we often take this information through these agreements with these individual institutions to try to look at their data from a perspective that helps them, because not everyone's the same. And so here's an example of something that differs across most hospitals, which is how their service, the contribution of service line across different procedure types versus robotics, lap, and open. And we can dive deeper and say, okay, let's look at other things like length of stay, readmission rate across these modalities, across this institution, and start to uncover insights that are very important. And in this particular case, we can look at length of stay and start digging down in to say there are best practices and then there are outliers as derived from this data. And if we can then go in and understand why these best practices are occurring and why these outliers are occurring, we might be able to pull individuals and uncover the problem. And that's exactly what happened here. But what often happens within this space is that it's not the initial hypothesis that you have. And so in this example, the idea is that by going in and observing the outlier surgeon who had a longer length of stay, it turned out that the ERAS protocols and patient transition order sets were actually the root cause for this. And by changing that behavior, which was accomplished by the medical center, you actually can have significant savings, as you see here, in terms of day bed stays. And that's across one procedure. And so by looking at data from this perspective at a high level, which is built on advanced analytics and other things like this, a little bit different than the imaging stuff, I think it allows us to be able to really dial in on what matters to a hospital in order to have evidence-based kind of change management right now. This obviously relies on what I mentioned before and what was mentioned by Dr. Stevens and others, is in terms of having a hospital accumulate enough examples across their robotic systems and their laparoscopic and open surgery cases, as well as Intuitive, to be able to understand how to navigate some of our data with their data. But I think it's resulted in some really interesting space that could even identify opportunities for where AI might bring maximal value within surgery.
Very interesting. I think we understand that Intuitive is also interested in improving the overall performances, and that might have an impact on the organization and the cost. But let's going back a little bit to the more specifically the robotic field, because I think this webinar is mainly addressed to the surgeons that are, as the surgeons, they're very focused on the operations and the way we can improve the outcome of the operation itself. And I would like to ask everybody a very simple question. Which are, in your opinion, the priorities? Because we understood today that there are so many different directions of research. Artificial intelligence might be used to solve specific problems in the medical act, diagnosis, images, or even doing a better microsuturing of a structure. This is a specific task. But if you would invest something, which are the priorities? I will start telling my own priorities with my perspective. I think the priorities, number one, is to improve the quality of the surgical operation, and through better enhanced intraoperative imaging and diagnosis. If you're looking at what happens around the world, the morbidity, the biggest disasters, let's mention just one: biliary injury. You know how many thousands of biliary injuries during a simple cholecystectomy they happen in a year in the United States? We are speaking about thousands, that with an incredible cost for the health system. How we can, and the majority of those injuries are connected with bad interpretation of the images, of the anatomy. So in my opinion, utilization of artificial intelligence in creating a new generation of images that are enriched, helpful in making a better diagnosis, or even connected with intraoperative pathology diagnosis. For example, understanding if a section margin of a tumor is a viable cancer-free section line or not. So I think this is my priority number one. Priority number two, in my opinion, is better coordination of functions inside the OR. I think we are wasting a lot of time simply with a longer turnover because the transportation is not ready, because the nurse is busy in another room. So having artificial intelligence coordinating different services and sending messages to the administration, recognizing a segmentation of the operation in a way that can give warnings that there are an average of 10, 15 minutes to finish this operation and everything is ready for the next one. And I think I put my last priority is not because it's the less interesting and fascinating and or less important, but I think in this moment probably is less urgent than the other is the automation. So having a system that is doing automatic step of a procedure or even completely autonomous is very fascinating, as Meren told, for the future, but I would invest on the other two. And now I would like to close the meeting asking everybody his own list of priority. Starting from Rick, that is not a surgeon, what do you think is the priority number one, in your opinion?
Well, I think your list is pretty good. Anybody who, I guess we're not flying right now, but anybody who used to fly would always have this experience of getting into the gate and not having the gate operator able to get over there, even though, for hours, the plane's going to arrive, right? So this idea that the surgery is getting ready to be finished and the post situation is not ready just seems an incredibly obvious thing to fix. We know from many people's work that improving communication and coordination and so on in surgery improves outcomes, and this seems to be something that, well, maybe it seems simple, needs AI, right? Maybe just the ability to monitor and to react in some more automated fashion, giving the surgeons and the surgical team better real-time tools that are not invasive, right, to coordinate. So I think that's a really great goal, and it's one that actually could borrow from many other fields. So I'd put that right up there. I mean, the automation is fascinating. That's a completely different problem, and
but
almost like you
what
want
about my priority number one? That is in increasing having a virtual augmented reality.
So I think this is one of the reasons why I put the AR in my example, because I think there is a huge leverage there as well. I mean, integrating modalities, augmenting it, curating it, and then getting it fast enough so that you can improve it during surgery. To me, is again, it's the reason I kind of pause on that a little bit is that there's a ton of effort, I think, going into that. And what's not clear to me is what the bottlenecks are. I mean, this deformation mapping that you mentioned, previously, of course, is one bottleneck. But it may be that we're going about it the wrong way, right? That what's needed is not what we're actually working on. And I think this idea of coming up with, if you were not biased by the current imaging modalities and by the current inability to integrate things, what would the surgeon actually want? right? And if we could maybe take a fresh look at it, because with AI, we can take a different approach to it. So I actually think that is an excellent one as well. But I think it needs a more fundamental rethinking rather than just powering on with the current approaches. So that's.
Okay, Maren, what do you think? Which is your list of priorities?
Well, Piero, again, we all come at it from a different perspective and priority. As you know, one of my passion has been telesurgery and remote surgeries. And certainly if AI can increase the applications of remote, especially in today's world of not wanting to move people from place to place and transport. I live in a country where 30% of population have to move to undergo any major surgical procedure. So if we can somehow improve that and include this, so this movement towards some reduction, I give you a simple thing, you know, people have to come down from small cities to undergo simple things like a mammogram, breast biopsy, prostate biopsy, etc. Can you use some form of AI-powered autonomous system which can do the screening? We do actually have MRI trucks which can go and do the screening, but they still have to come back down for the biopsy. So you can imagine AI-powered systems which can actually detect and deal with the biopsy and diagnosis in these remote settings. So actually I have put in for a large grant from the federal government to do that, because I don't think building simple things like that are that difficult. I'm working with companies which are already working on AI radiological platforms for imaging and detecting lesions in the breast or prostate. You can see that you can significantly enhance quality of patient life if you can develop simple AI-powered robots which can detect and biopsy and potentially even ablate lesions in one setting, avoiding the need for transfer travel, undergoing more so resective surgery in OR. So I do think that simple AI-powered robots may actually change the point of care and even approach to care. I know a big part of Intuitive's business is prostatectomies, but I think I can see an AI-powered systems which can detect and treat early prostate lesions and avoid a resective procedure in future. So I think you know, companies have to be alert that AI-powered system may disrupt the way we operate and disrupt the approach that we are currently taking, because we are doing it based on our manual systems. And so I do see that investment, as Rick said, is important, because you can't do any of this without, right? And I do think investment, it's not just companies which have to invest. I think agencies and governments have to also invest. Fortunately, in my country, this is an important area because of the nature of the country I'm living in, that there needs to be an increasing investment being made. But it is required. It's billions and billions of dollars required to bring this to fruition. So my hope is that there is work on how AI can change the pattern by which some procedures and some surgical techniques are being conducted, because I don't think everything is going to be done the same way in future.
Thank you. Leo, very briefly, which is your priority list?
You know, I totally agree with you. I think the imaging definitely the first one, right? I mean, if you look at the 3 tiers of robotic surgery, right? Surgeon, robot platform, and visualization, right? Of course, you know, 3 of them, all of them has to be good. You know, one of them get done, you don't have a good surgery there. But the problem is that for the robotic platform there, things could be changed. For example, you know, if for 5 years now the soft robot system dominates the market, well, I'm probably not that quickly, but And then the training, the surgeon training part will be different. But no matter what kind of surgery platform, the visualization part, it stays there, right? So that's why I think the molecular imaging, we'll talk about this biopsy. I talk a lot about this one, right? But the problem that I'm not a physician, but my feeling that, your biopsy, your AI biopsy works great, 100% better than the other thing. The problem that if you biopsy a wrong place there, it doesn't matter as how good your biopsy there is a wrong result. So I think, to enabling the molecular biology and do the to enable it, the biopsy and the actually imaging, do the pathology in situ, in vivo, as the way to go. So I think, I absolutely agree with you. The imaging, especially the molecular imaging, has to be the priority number one.
But in fact, we are speaking about digital image-based surgery. So I think the images should contain all the information that we need to do the perfect operation. And I think we have to finish because you, Anthony, learn from the others which are the priority. And the question, if you can disclose that, of course, which are the priorities of the company?
So I'll speak personally on this from my perspective, which I think I broadly align with what was said here. But given my history in terms of the work that I'm doing, I would actually put number one as investing in spaces that improve current methods of surgical training and education, or care team training and education. And the reason is that I think that actually requires us to develop a deep understanding of what's actually happening in surgery, where the pain points are, where the inefficiencies are, and how we can surround with tools to kind of potentially enable improvement there. I would then put number two as intraoperative guidance. So now that we've uncovered new ways to potentially train surgeons and identify context of where things are happening in surgery, how can we pull in molecular imaging agents, preoperative images, things that we at Intuitive are working on, and many other companies are working on, to be able to improve performance. And sometimes that does involve, I think, augmenting a surgeon's decision making by highlighting anatomy that is not to be touched, or highlighting anatomy that should be removed. But it also is in the basic form that you mentioned, Dr. Giulianotti, which is maybe giving just general awareness to the OR about what's happening and when other things are happening to impact workflow and that sort of thing. And then I think lastly, and these are always hard, but I think diagnostics. So Dr. Anvari mentioned these sorts of things, but I'm personally excited by the ability to diagnose much earlier, so that then the treatment path can be influenced or changed. And if you look at the ION platform that Intuitive has been working on and building, it has many exciting capabilities powered by surgical AI to be able to segment the airways of a lung and provide augmented reality environments to navigate and help predefine paths to get to these distal nodules. So those would be the three areas that I would think align with my prioritized list.
So basically, we are on the same page. Even though, let me reiterate that you can train someone to do a cholecystectomy, and so investing on training, of course, is an important part. But if the surgeon don't recognize the anatomy, he will learn to do mistakes, because a misinterpretation of the anatomy will lead to awful mistake. And you have a powerful platform that can do terrible mistakes at that point, because you have a powerful weapon. But if you are unable to recognize the target, you can do wrong. So in my opinion, we have to improve the intraoperative visualization, really including enhanced way or virtual way of seeing, and then of course the training, the virtual training. So we are a little late. I will close this very interesting webinar, and I'm thanking you all for your participation, and we'll organize something soon on the same topic. So thank you and have a good day.
Thanks very much.
Thank you
Very much.
Bye-bye.
Bye.